Okay, let's talk about derivatives of logarithmic functions. And here I just wrote the two rules for basic log functions. If you have log base b, so like log base 3, or anything other than a natural log, then your derivative is 1 over x times the natural log of whatever the base is. So you have to remember that in the denominator, you multiply the 1 over x, the x in the denominator, by the natural log of whatever the base is. That was a terrible job of circling. There, that's better. If it's a natural log, then the derivative is just 1 over x, and the reason you don't have the natural log component in the denominator of the derivative is because a natural log is log base e of x, and so if you followed this top rule to a t, then you would multiply the denominator by the natural log of e, but you should know that the natural log of e is equal to 1. And so we are technically following this full rule up here for the natural log case, but in the case of natural log, you're multiplying the denominator by 1, and so the derivative of natural log x is just 1 over x. It gives you less to have to think about, which is good because more often than not, we are dealing with natural logs in calculus rather than logs of other bases. So let's do a few quick examples. And so here we're doing the derivative of x cubed plus all this stuff. Log base 2 of x, so the derivative of x cubed is 3x squared, and then here's the new part, the derivative of log base 2 of x, it's 1 over x, and then you multiply the denominator by the natural log of whatever the base is of that log. So number 2, derivative of cosine x is negative sine x, and that's one y'all should know just for memorization. The derivative of natural log x is 1 over x, and you're done. That's it. You don't have to put a natural log of anything in the denominator if you're doing the derivative of natural log x. Number 3, the derivative of e to the x squared plus log x. Okay, so here I snuck a chain rule in for the e part. Inside the e is an x squared, so the derivative of e to the x would just be e to the x, but in this case there's an x squared, so we have to chain rule that, so I need to multiply that by the derivative of the exponent. So the derivative of x squared was 2x, so 2x e to the x squared, and the derivative of log of x, that is not a natural log, that is a log with a different base, and if no base is written, then it's understood to be a base of 10. So your derivative of number 3 is 2x e to the x squared plus 1 over x natural log 10. And then one more example before I uglify our natural log derivatives. So the derivative of the natural log of x squared plus 1. So you notice in this one, I made the inside a little bit uglier. It's no longer just the natural log of x, which I know the derivative of natural log x is just 1 over x. This is the natural log of something uglier. And so what I've done here is I've created a chain rule with my logarithmic derivative. And so I'm going to start off by ignoring the inside, which is what you do with chain rule, and the derivative of natural log x is 1 over the x. So I'm going to do the exact same thing here. The derivative of natural log stuff is 1 over the stuff, which in this case is x squared plus 1. But once I do the derivative of the natural log, then I need to multiply that whole thing by the derivative of the inside. So now I'm going to chain rule by multiplying by 2x. If you have 1 over something times 2x, you could rewrite that a little bit more cleanly as 2x over x squared plus 1, and that would be your derivative of the natural log of x squared plus 1. So now that I've shown you a chain rule inside a natural log derivative, so here is a rewriting of your derivative rules for logs. So if we include the chain rule, the derivative of a natural log, or I'm sorry, of a log is 1 over x times the natural log of the base, but then we have to multiply by the derivative of what was inside the log. So actually I'm going to draw the arrow right here because we're doing the derivative of what was inside the log, and that's how we got f prime on the outside. So it's 1 over stuff, natural log b, times the derivative of the stuff. Same thing for the natural log. The derivative of natural log is 1 over the inside, so it's 1 over f, but then we have to multiply by the derivative of what is inside. That is your chain rule. Now, in the case of logarithmic derivatives, it's 1 over stuff times the derivative of the inside. That can be rewritten as f prime over f, and then the natural log of the base of the log in the denominator. So I will almost always, from now on, I will almost always jump straight to this for the derivatives. I'll skip that middle step where I do 1 over and then times the derivative of the inside, and I'll just put the inside derivative on top. So let's put that into practice a couple of times. And so if I'm going to do the derivative of log base 3 of this stuff, I know the derivative of log base 3 is going to be 1 over the inside. And because that is not a base of e, it's not a natural log, I need to multiply the denominator by the natural log of the base. So I'll multiply by natural log 3. But then the derivative of the inside ends up going on top. And that is your chain rule. So I'm going to put the derivative of the inside on top. And so there is our derivative. That doesn't look like it simplifies any, so we'll just leave it like that. The derivative of the natural log of secant x. Well, now it's natural log, so in this case, we don't have to worry about putting an ln something in the denominator. So the derivative of the natural log, it's 1 over the inside. And then the derivative of the inside goes on top, and the derivative of secant x is secant x tangent x. And in this case, which is often the case when there is trig functions incorporated into a natural log, we can simplify. The secant x's actually cancel, and your derivative cleans up to a nice, clean tangent x. And so there is our derivative for number 6. And I have one more example I want to do, and I'm actually going to do this example twice for the sake of making a point. So here I have a really ugly logarithmic derivative. It's the log of, or the natural log of x times the square root of x squared plus 1. So when I do that derivative, I know that the inside is going to go in the denominator. So I'm going to go ahead and put x square root, except instead of writing square root, I'm going to write x squared plus 1 to the 1/2. Then I need to do the derivative of this function and put it in the numerator. And so if you need to, go off on scratch paper and think, if I do the derivative of x squared plus 1 to the 1/2, what I have here is a product rule. I have x times all this stuff, and in this product rule I actually have a chain because I have ugly stuff to the 1/2. So when I do the derivative of this piece, the product rule is derivative of x, leave the second one alone, plus, now I'm going to leave the x alone, and then the derivative of the second is going to be a chain. We're going to bring the 1/2 down, leave the inside alone to the negative 1/2. Then I multiply by the derivative of the inside. The derivative of x squared is 2x. And all of that is going to go in the numerator because that's the derivative of what was inside my log. So 1 times stuff is just going to be x squared plus 1 to the 1/2. And I'm looking at this second piece, and there's a little bit of simplifying we can do because this, if I look right here at all of that, it's all multiplication, and I see that half of 2 would end up giving me 1. So those multiply to give you 1, and then I have x times x, that'll be an x squared. So I'm going to multiply those to clean up to an x squared. I still have x squared plus 1 to the negative 1/2. And for now, we'll stop here. There is some simplifying and some factoring we can do to clean that up. But for now, let's stop there with this approach to number 7. And I did do this as difficultish, whatever. I did do this very difficultly. I hate that word. Because I jumped straight into the calculus, and I have told you before that before you just dive into the calculus, always stop and think for a minute, is there anything that you have learned in the past that we could simplify my function to make the derivative a little bit nicer? And in this case, you can. So I'm going to look at number 7 again, only I'm going to make the calculus significantly easier by using 3 properties of logs that you learned in a previous life. And at one point you learned that if you have a natural log of a product, that can be written as the sum of 2 logs. So the natural log of a times b is ln a plus ln b. If you have the log of a quotient, you can split that log into subtraction. So the natural log of a minus the natural log of b. And then if you have the natural log of a to any exponent, that exponent, if it's only on the argument, now the whole log is not being raised to a power, it's just the argument, it's just the a, I can bring that x down times the natural log of a. And those are things that you learned in Algebra 2 and you learned again, reinforced in pre-cal. Unfortunately, in pre-cal, you do this in the first 9 weeks of the year, so it's been about a year since you've seen this, but you need to go back and polish these up and remember these properties, because for this example, ignoring the derivative part, I can clean this up because I have the natural log of x times something, which means I can rewrite that as the natural log of x plus the natural log of, and I'm going to change the square root to stuff to the 1/2, so x squared plus 1 to the 1/2. And in doing that, I now have eliminated my product rule. So there is no longer a product, it's natural log of x plus natural log of stuff. But I'm not going to stop there, because I see now that I have a natural log, and this argument of x squared plus 1 has an exponent. So just like I pulled this x to the front right here, and made it a coefficient of the log, I can do the same thing with that 1/2. So I'm going to take that 1/2 and put it in front, and now my derivative, notice I haven't done any calculus yet. These are all properties of logs that you learned in Algebra 2 and in pre-cal, but I can rewrite the function that I'm differentiating as the natural log of x plus 1/2 natural log of x squared plus 1. And now there is no longer any difficult calculus. The derivatives that we're going to do here are very straightforward. I've eliminated the product rule, and I've eliminated that ugly chain with x squared plus 1 to the 1/2. So now when I do my derivative, if you are adding, you do the derivatives completely separately. So we're going to separate these two. The derivative of natural log x is just 1 over x. Plus, and if you have a constant, I have 1/2 times natural log, you can ignore the 1/2, and the derivative of natural log of x squared plus 1, the x squared plus 1 goes on bottom, and the derivative of that goes on top. And there is a derivative for the 7th example we did. So if you look at this, I did a little bit of harder work at the beginning. I did some pre-cal, I did some simplifying, but the trade-off was that I made the derivative significantly easier. Going from this to that, the actual differentiation step was significantly easier than all of this stuff we did here, or at least in my opinion it was. So when you have natural logs, go ahead, the second you see a natural log, turn on the part of your brain where you have these properties, and these are the main 3. There are other properties, but these are the main 3 we're going to use. And think for a second, can you use these properties to split up and simplify your logarithmic function? And if you can, it'll make the derivative a good bit easier for you.